Welcome back, and now we are headed to the last lecture of the series by Matt Hogancamp.
Cool. Okay, thank you everyone. I'm just going to erase this board and maybe copy these relations over on the left board.
Maybe during that time, quick announcement that this is the end of our activities this week, but next week on Monday at 11 a.m. here at IMPAN, but not exactly this room, one floor up, there will be a seminar given by Omar Al-Ghazali. It will be about, can you give us the title?
A combinatorial theory of knots.
Okay. So, hope we will welcome you on Monday.
Cool.
Yes, there will be an email. It will be also on the website. Great. With the room number. I think it's 403.
Okay, I've just copied down the relations from last lecture over here on this board, so we can refer to them if we need. So just from these relations only, we can compute the Kovanov-Brzezinski homology of all positive torus links. So I need to tell you what a torus link is. Let me say maybe just right now before we get too deep into it. So these, in principle, one can use these relations to compute, or at least get most of the way towards computing lots of examples. So obviously torus links are a very special class of links that one may or may not be interested in. So it's a kind of a natural question. Can you use these relations to compute homologies of other knots, other links? And the answer is, it depends. I mean, yes, there's lots of things that can be computed in this way. It's just that the torus links are a particularly interesting application because they were the subject of so many conjectures. The reason many people were interested in torus links is there were lots of conjectures relating these homologies with other kinds of gadgets appearing in algebraic geometry, representation theory. Anyway, and so there were like other reasons, like independently reasons that we wanted to compute these things. And I'm not sure the best way to motivate these sorts of things from a physics perspective. I might leave that to other people, but I just want to say there were many reasons for us to consider this family of links. Anyway, so what is a torus link?
Maybe I would just say that usually it is the simplest family.
It's the, yeah.
This is a good reason.
It's a good reason, yeah. They are, so there's an operation in knot theory called cabling where you take a knot and then inside a neighborhood of that knot you replace you replace inside a neighborhood, so you replace, so there's an operation called cabling. So what happens? What does this mean? So you take a knot, and now you imagine replacing your string with like a hose. So now it's a knotted sort of tube. And inside the tube, you can then draw any other knot. This operation is called cabling. And torus knots are cables of the unknot. They're sort of particularly nice cables of the nicest knot. Yes, they're in that way, they're the simplest family of knots. Okay, so choose integers n and m, and for us they're going to be non-negative. So here's how you draw a torus knot, or link. So these will be, the number of components is going to be the greatest common divisor. So I'll draw a link, and the number of components of the link is going to be the greatest common divisor. So I'm going to draw n points on the bottom of the cylinder and m points on the side of the cylinder. And all we're going to do is connect the dots. So these guys connect to those. And then everywhere else we connect the dots around the back of the cylinder. So we get in this way a braid on n strands, and when you close up that braid, so the braid is clearly embedded in the surface of a cylinder. So when you close up, the resulting link or knot is embedded in the surface of a torus, which is why these are called torus knots. If n or m was negative, then instead of going up and to the right, we would go up and to the left. We would wind around the opposite direction. In this talk, we'll only be talking about positive torus knots and links. So they'll wind to the right. There's a slightly more convenient way of writing. So it's not clear from this picture, so this defines a link called TNM. It's not clear from this picture, but there's a symmetry. So TMN is isotopic as to TNM. It would be nice to have a description of it would be nice to have a diagram in which the symmetry is manifest. And if you want a diagram where the symmetry is manifest, what you should do is you draw m strands. In this case, m is 4, and n strands. And you just sort of cross them, you see. And then the closure of this turns out to also be TNM. Etc. So this is also TNM. And then the symmetry between n and m is a little bit more clear because you can kind of rotate this whole picture in the z-axis and exchange n and m. Okay. I'll leave it to you guys to think about why this is still the torus knot. But I'm happy to say more if you guys are curious. Maybe just to kind of ruin my exercise a little bit. This may not look like it, but this is actually a picture, this surface. So what I've drawn here is a surface embedded in R3. And it may not be entirely clear, but in fact this is homeomorphic to the standard torus, just the standard kind of donut sitting inside R3, unknotted donut just sitting in R3, minus a disk. And so the fact that we can draw this knot, we can sort of clearly embed this diagram inside this surface. Therefore, this diagram sits inside the standard torus. Therefore, it is a torus knot. And which torus knot can be deduced just by computing how many times it winds around. So that's the proof of this exercise, given this exercise. Okay. So in order to compute, so think about this. So I want to compute the Kavanaugh-Brzezinski homology of such a diagram. Step 0 in such, to kind of initiate the algorithm, we choose a strand and we place a K1 somewhere. And then at each step of this sort of procedure, we want to do one of the, perform one of these operations. So what we want is we want a family of diagrams built up out of braids and little boxes, which can be sort of simultaneously kind of computed using these relations. So what I want to do is describe for you a family of diagrams constructed from certain kinds of braids, including those as a special case, built up out of braids and boxes, and for which you can reduce monotonically in some sense using these relations. So the family is going to be indexed by pairs of binary sequences. So we'll consider sequences V and W. So V is going to be a binary sequence of length n plus L, let's say. W will be a binary sequence of length m plus L. And I want the number of ones inside V and the number of ones inside W to be equal. Actually, sorry, I don't really need, I'm sorry, plus L. So just pairs of binary sequences, the length of each sequence, the lengths of each sequences are unrelated, but I want the number of ones. So absolute value sign means the number of ones. So to each pair of binary sequences, I want to define a diagram. And each diagram is going to correspond to a certain complex of bimodules by the procedure we have talked about already. Okay, and so I'm going to define this by example. Okay? So the example I want to start with is where V is, let's say, 1, 0, 0, 1, 0, and W is 0, 1, 0, 0, 0, 1, let's say. So what we're going to do is, very roughly speaking, so if you're taking notes, don't draw this quite yet. Very roughly speaking, we're going to connect the ones down here to the ones up here. And then we're going to connect the zeros, or they're just going to go off to the side. And then we will put crossings in so that these are all sort of positive crossings in the braid group. And we'll put a projector which sort of clasps together the one labeled strands. This is the basic idea. So let me redraw this picture a little bit more carefully. So the size of the projector, I called it a projector, the size of this K2 of this little box is the number of ones. So in this case, it's just 2. And here we go. So I'm going to draw so each of these 4 zeros connects to some distant kind of point over here on the top right. And then each one of these ones connects into this white box. And then we do the similar picture, making sure that all the crossings are right-handed as we do this. clear enough. And then we close up, which I won't picture, but we'll close this up like by connecting the top boundary points to the bottom ones. And that's so this represents our complex of bimodules, and then when we close it up and compute homology or whatever, this will be the homology that we want to kind of compute inductively using those relations. Okay. And sometimes it's useful to kind of color code the strands. So I have colors, I have lots of colors. I'm going to draw the projector, the strands which are labeled by 1, I'm going to color them red. It's a little bit misleading because the strands are not necessarily all distinct. So I'm coloring this one blue because it is associated to 0 right here. However, when you close up, when you connect up the top and the bottom, it's going to connect to the red strand. So the red and blue have no meaning once you kind of close up and take homology, but they're useful. It's a useful device just for applying the relations that we were going to use over there. Okay. And so the main computation, oh, and notice, so how do we get the torus knot? Well, if V and W are all zeros, so D 0 to the N, so if you take the sequence of N repeated zeros and M repeated zeros, then you just recover. You recover the diagram that gives you the torus knot. So this guy really is a special case of those diagrams. And in fact, if you had 0 to the n minus 1, comma 1, 0 to the m minus 1, comma 1, this picture would also be so I claim that this picture is also a diagram for the torus knot. And the way that you see it is by introducing a Reidemeister 1 kind of equivalence. So the sequence where you have all but one of them are zeros and then the 1 in both slots, that diagram is equivalent to this diagram. Which again is the diagram for the torus knot. So if both V and W are all zeros, then you get the sort of standard diagram for the torus knot with no little boxes inside of it. And then this light modification gives you a diagram which has a distinguished little white box. Okay, well. Okay. So now what we're going to do is we're going to...
It's not super smart, but how in practice should I... not in practice, I mean for this computational things, should I think about the box? Because I remember the assignment of this KN.
Yeah. So...
Is there some shortcut for it?
So there's kind of a shortcut. So this is how you should be thinking of this. Now I'm going to try to keep this very brief, and which means I'm going to say things that I haven't defined or talked about yet in this lecture. But we all like diagonalizing things, I think. So from this perspective, let me kind of motivate what this little white box means. So So decategorified, so in the categorified level, we have these bimodules and complexes of bimodules. Decategorified, these all correspond to elements of something called the Hecke algebra. And inside the Hecke algebra, this is an element of the Hecke algebra on 2 strands. It has some eigenvalues. It has eigenvalues. It depends on your choice of conventions here, but let's say the eigenvalues are 1 and q squared. Or, yeah, 1 and q squared, okay? In general, you can consider the full twist on n strands, so that's pictures of this sort. And the eigenvalues are one and then a bunch of others. So it's the eigenvalues are indexed usually by partitions of n. Some of them maybe coincide, so it might be, you might accidentally get, so they're indexed by partitions of n, but some of them actually may coincide. So this is the eigenvalue associated to this box, or this partition. This is the eigenvalue corresponding to that partition. And the point is, there's a distinguished element obtained by taking all of the partitions of n which are not equal to the box. And what you do is you take the full twist minus that eigenvalue. And let's give the eigenvalues names like sigma sub lambda. Okay, so this is a thing which is not quite a projection operator because you haven't normalized it correctly. But it will project onto the one eigenspace. And the box Kn is a categorification of this. It's a thing which is not a projector. It's not an idempotent operator because you haven't normalized it correctly. However, it will project onto the one eigenspace of this full twist guy. And the relation here is actually some standard relation between the projecting onto the one eigenspace of the full twist on n strands and projecting onto the one eigenspace of on n plus 1 strands.
Okay, thank you.
I hope that was helpful. Thank you for the great questions. And if I'm not answering your question now, then let's I'm here for a while, so we can talk later. I hope at the very least this just sort of stirs up some sort of thoughts, and we can have conversations about this later. Okay, so here's the family of diagrams, and how do we use these relations to compute their homologies? So there's 4 cases, basically. We just want to read it's very simple. We just want to read the diagrams from left to right. And one of 4 things occurs. Either both sequences begin with a 0, or one starts with a 0, one starts with a 1. These 2 cases will be almost identical because of the symmetry. There's an evident symmetry in these pictures. You can just rotate or flip top to bottom. Or they both start with a 1. Okay? So in each of these 4 cases will correspond to just one of these relations, basically. So this one is actually the most complicated, so we'll do it last. We will do this one first because it's easiest, and then this one, and then this one. And these 2 are really similar. Okay. So let's draw a picture where both of the sequences start with 1. I'm just gonna okay. It's not complicated enough. Let's do this. So let's say these are our sequences, just to have an example. And let's draw the corresponding picture. So you guys have the so you can all visualize what's going to happen here. I think. So we'll have a box of size 2 because we'll only have 2 1s. These zeros, I am not sticking with my color coding. Sorry. Maybe I should. And then we've got some blue strands. And it's red strand. And some blues. So in such a diagram, because both of the sequences V and W begin with a 1, this red strand on the very left gets connected to itself in the closure. And so this is just a very easy application. It's a direct application of relation 3. So so this guy simplifies immediately to just a sum of copies of. So if the number of 1s inside V, which is the same as the number of 1s inside W, is L, maybe I'll just label it. I'm sorry. Maybe I'll just label it this way. So that's a very easy application of 3. So we've simplified. So it simplifies this pair of sequences. So we want a relation which sort of monotonically decreases the complexity of V and W.
The exponent should be inside the bracket.
Sorry. Yes. Okay. So what about these two? So let's draw an instance of this.
Yeah, you can erase the already made photo.
So again, just picking some random sequences. So let's say V starts with a W, or V starts with a 0, but W starts with a 1, let's say. Okay. So then we draw So that's our diagram. And what do we do to simplify this? Well, really what's going to happen, so when we close up, we're really only interested in what's happening kind of here in the left part of the picture. So when we close up, if you ignore this box here, which we see an opportunity to do a Reidemeister 1 move, because we see this this bit of diagram. So we want to simplify our diagram using this like Reidemeister 1 move, okay? So that's, but in order to make that happen, we have to slide the box so that instead of it being here, we have to kind of move it out of the way. So I know this may mess up Piotr's pictures. You took a picture of this already, or no?
No, yeah, sorry.
No, it's okay, it's okay.
It should be that interactive. Yeah, let me make it. Done.
And then, so what we'll do is we'll slide the box. So this is a relation which can be formed on these complexes. You can slide the box kind of out of the way, so now it lives here. And now you do the Reidemeister 1 move that you wanted.
Done.
And what you see is this type of picture. Okay. So that's, but there, remember this box, this K thing will absorb crossings. So I'm gonna modify it again.
Okay. Done.
So this absorbs those crossings, and you can redraw. In this way. And so now basically what we see is that the two indices have been deleted, except for like this one, which used to be this strand, which used to correspond to a 0 of V. Now it hits this projector. So now this strand is colored red. And it corresponds to a 1 of W. So the statement is that, so we started with something of this form, and what we saw was that the 0 gets deleted, and the 1 cycles around to the back. Do you believe it? By symmetry, this guy will simplify in the exact same way. So the 0 gets deleted, but the 1 cycles around to the other side. Again, we've simplified the pair of binary sequences by decreasing the length of one of them. Now for the last relation, we're going to have to use this relation, so we'll get a pair of terms. This is what makes this a little bit more interesting than the others. So let's start with just a random pair of sequences, both which begin with a 0. Say, okay. And now we drop. So the 0s, W, and the 1s. Okay. So pretend you're writing this paper. You're like, what do you do? How do you simplify this? Well, how do we do the other ones? Well, we remember that these are really, we want to close, we're closing up and taking homology of this picture, and we're allowed to use the Reidemeister moves, and we're allowed to use those things 1, 2, and 3. So again, kind of what do we see? This leftmost strand here is this blue strand. We see a place where we could do Reidemeister 1, right? And then what are we going to? What's the result of doing Reidemeister 1? Well, this strand wraps around the projector. There is this Reidemeister 1 opportunity, but it also wraps around the projector. So when we simplify this, this is going to challenge my ability to draw these pictures.
Should I make photos in real time or wait until we...
You can wait until, I won't change this picture, but I might modify this one a little bit.
Okay.
We'll see. I will, this one is the most complicated, so I think it might be important to have like each step of the computation available. So I'm just going to redraw the same picture and then change it and then modify. It's needed. This is where iPads are better than chalkboards, but that's okay. Because we can copy and paste on an iPad. But. Okay, and then when we do the Reitermeister 1, let me, well, I'll just remember the index. So we do this Reitermeister 1 move. And then the picture we see is, so this blue strand, well, maybe I'll write it like this. Okay. And so we see an opportunity where we can use this relation 3. So what I will do is I'll circle the place where that relation is going to be relevant. Okay, and what are the two terms in that relation? Well, one of them is going to have a bigger projector, I guess on 4 strands. Okay, so one of the terms is going to be this. And you see this diagram is of the same format. Basically what happens is these zeros get cycled around to the back and where they become ones. So the first term in this simplification is a dv1 w1. And the second term in the recursion is, well, instead of having a projector here, you don't. You just unclasp. And I claim so this one is a little bit more interesting. So let's redraw this picture. We're going to do some Reitermeister moves. Oh boy, okay. So I don't know if this is, hopefully we're all on the same page currently. Let me redraw this picture. Sorry, this is a mess. Sorry, I'm just gonna modify this picture. So what we're gonna do is this strand right here. I'll color it orange. So this strand right here. Up to isotopy, we can draw it on the other side, so that it goes. So I'm dragging it via an isotopy. Okay. And now I do the inverse of the Reidemeister 1 move. And I remember that I'm not drawing all my closing strands. So have you taken a picture?
Just one moment. Yep.
Okay. So I don't need to draw all of my closing strands. So what this picture is this corresponds to the situation where I have a pair of zeros here and here. So one of the terms is dV1W1 and the other term is dV0W0 with this shift and an overall shift of t squared q squared, or q to the minus 2 to the size of v, or negative that, whatever. So there's a overall shift that, I think that should have been a minus n, I apologize. You guys should read the actual paper for that careful shifts. And have we done it? Have we made this diagram simpler by writing it in terms of these things? Well, we haven't decreased the length of either sequence, W or V, but we've in some sense made, this term is in some sense simpler because it has more ones. So we can just declare that the simpler sequence, like increasing the number of ones without increasing the length. We've decreased the number of zeros. So like in that sense, we have made this sequence simpler, or these pair of sequences simpler. This one, on the other hand, you might wonder, is it actually simpler than that sequence? You need to wonder these things if you're going to write an algorithm. Does it terminate? Okay. So what could possibly happen here? So if you keep reading your pairs of binary sequences, V and W, and each one of these relations will strictly simplify your sequence, your pair of sequences. And maybe this one doesn't. So the only sequence for which this doesn't strictly simplify is the all zero sequence. Like, what move are you going to do exactly like next after this one? Well, you're going to either do this one again, fine, or you'll do one of these three. And the only issue that could arise, the only way this algorithm could fail to terminate is if V and W were both the all zero sequence. That's the only way that this algorithm could fail to terminate. And if V and W are the all zero sequence, then you use relation 0, which is having the all zero sequence means you don't have a K1 anywhere. You don't have a box K anywhere, so you just reinsert it. Anyway, so in that way, this does terminate as long as you have to like treat the all zero sequence a little bit specially. And that's it. So this is how you compute. So the theorem is that the super polynomial of positive torus link, or this Poincare polynomial of Kavan-Rorzhansky homology of a positive torus link can be computed by this recursion. Okay. So anyway, so I think that's all right. Let me just say that many people possibly in the audience here or online are interested not just in Kavanaugh-Jarzynski homology, but in colored Kavanaugh-Jarzynski homologies. So I know that you know, there's this very interesting Knots-Quivers correspondence, which knows about not just the Kavanaugh-Jarzynski homology of a knot, but also its various colored versions. And I won't go into any details because I'm like really out of time, but these, as I kind of alluded to, these little boxes that we are placing in our diagrams, they correspond to some kind of symmetrizers, or like symmetrizing idempotents, except that they're not quite idempotents, you know, they're not properly normalized to be idempotents. But one way that we compute colored homology is by cabling a knot and then inserting a certain idempotent somewhere in that knot and computing homology of that, or computing the invariant of that. And so one consequence of this whole setup is that we can actually achieve a computation of, with only a slight repackaging, we can compute row colored. So the colors they correspond to Young diagram shapes, and because this is particularly well adapted to the symmetrizing or the one row partition, we can compute this colored homology of torus knots. Basically in the same exact way. The only thing is that you must start with a sequence which is like 0 to the n minus 1 d, 1 to the d, 0 to the m minus 1 d, 1 to the d. You start with a different initial sequence, and the same exact recursion will compute its colored homology. So I don't know. I mean, I think it's a fun game to play, and now you can go on and compute things if you wanted to give it a shot. All right, that's all I have time for. Thanks, guys.
Okay, maybe one quick question.
When you're computing D0V and 0W for the relation, while you were drawing the diagram, yes, that first one, you used, I think, relation 3, or was it 2? When
It was 2. It was, well, it's, yeah, I'm sorry, they're relabeled, but it's equation 2.
Equation 2. Okay, thank you. That's what I thought.
Okay, okay. Plus some Reidemeister moves or their inverses.
Yeah, we should
Vacate?
we should leave the room. So maybe
Okay.
let's move the rest of the discussions like to outside, and thank Matt for the whole lecture.
Okay.
I'll stop the recording.